73 seconds after liftoff, Space Shuttle Challenger tore apart in a clear Florida sky. 7 people were killed. But the fatal sequence did not begin in the air. It began years earlier, inside a rocket joint engineers already knew could leak, and in a conference call the night before launch, when specialists warned that the cold made failure more likely. The warnings were there. On January 28, 1986, Challenger stood at Launch Pad 39B carrying mission STS-51L. Its crew included Commander Francis Scobie, pilot Michael Smith, mission specialists Ellison Onizuka, Judith Resnick, and Ronald McNair, payload specialist Gregory Jarvis, and teacher Krista McAuliffe. Millions of Americans watched because McAuliffe was meant to teach lessons from orbit. The launch had already been delayed several times. Overnight, temperatures at Kennedy Space Center fell into the teens. Ice formed on the launch structure. At liftoff, the air temperature was 36 degrees Fahrenheit, 15 degrees colder than the next coldest previous shuttle launch. The shuttle system depended on 2 enormous solid rocket boosters. Each booster was assembled from steel segments joined together at circular field joints. Inside each joint sat 2 rubber O-rings, intended to prevent burning gas from escaping. When the booster ignited, pressure made the metal casing flex and the joint gap open. The O-rings had to move quickly enough to keep that gap sealed. That design had troubled engineers long before Challenger. During testing in the 1970s, the joints rotated more than expected under pressure. NASA and contractor Morton Thiokol added a second O-ring, but the basic joint still relied on flexible rubber responding in a fraction of a second. In actual flights, inspectors found erosion, scorching, and soot where hot gas had passed the primary seal. After the cold January 1985 launch of mission STS-51C, both boosters showed O-ring distress. One Thiokol memo warned that the seal problem had become acute. Yet the shuttle kept flying. This was not proof that the danger had disappeared. It was evidence that the system had survived repeated warnings. The Rogers Commission later described how NASA and Thiokol gradually accepted erosion and blowby as an unavoidable flight risk. Each successful mission made the abnormal seem normal. Physicist Richard Feynman called it a kind of Russian roulette. Getting away with a risk did not make the next attempt safe. Cold made the problem worse. Rubber loses resilience as temperature falls. A warm O-ring can spring back as the joint opens. A cold one responds more slowly and may remain compressed while hot gas finds a path around it. The Commission found that a compressed O-ring at 75 degrees was 5 times more responsive than one at 30 degrees. On Challenger's right booster, the coldest part of the suspect joint was estimated at only 28 degrees, plus or minus 5. On the evening before launch, engineers at Morton Thiokol examined the forecast. The predicted temperature was far below their previous launch experience. In a teleconference with NASA, Thiokol initially recommended not launching below 53 degrees Fahrenheit. Engineers Roger Boisjoli and Arnie Thompson argued that low temperature could delay O-ring sealing. Their evidence was incomplete, but the uncertainty pointed toward caution. There was no flight data proving the joint safe in such cold. NASA managers challenged the recommendation. They wanted a technical basis for the temperature limit. During an internal Thiokol caucus, management reversed the company's position. The written no-launch recommendation was replaced with approval. The engineers who continued to object were not included in the final decision presented upward. Senior launch decision-makers were not told the full history of O-ring damage, the contractor's initial recommendation, or the continuing opposition inside Thiokol. Another warning came from Rockwell International, the shuttle's orbiter contractor. Ice covered parts of the launch structure. Rockwell representatives worried that falling ice could damage the orbiter, but their concern was not communicated as a firm no-launch recommendation. The commission later concluded that the decision-makers did not clearly understand Rockwell's position either. At 11:38 a.m., Challenger lifted off. Launch cameras later revealed black smoke near the aft field joint of the right solid rocket booster almost immediately after ignition. The cold O-rings had not sealed properly. Hot gas escaped, but aluminum oxide produced by the burning propellant may have temporarily plugged the leak. For nearly a minute, the fragile seal held. Then the shuttle encountered strong aerodynamic forces. Around 58 seconds after liftoff, a flame appeared from the right booster. It grew and struck the external fuel tank. At about 72 seconds, the lower attachment between the booster and tank failed. The booster pivoted. The external tank began to break apart. At 73 seconds, Challenger was engulfed in a fireball and disintegrated under aerodynamic loads. The vehicle had not been destroyed by a mysterious explosion inside the crew cabin. The accident sequence began with a failed pressure seal in the right booster's aft field joint, a design the commission called unacceptably sensitive to temperature, dimensions, materials, reuse, processing, and dynamic loading. The technical failure was only half the story. The Rogers Commission found that the launch decision itself was flawed. Information moved unevenly through the organization. Engineers saw a dangerous pattern, but managers demanded proof of failure instead of proof of safety. Past damage was reclassified as acceptable because previous flights had survived. Schedule pressure and organizational habit separated the people making the final decision from the people who understood the hardware most intimately. After the accident, shuttle flights stopped for nearly 3 years. The solid rocket booster joint was redesigned with stronger capture features, improved seals, heaters, and stricter inspection. NASA also changed parts of its safety and management structure. The shuttle returned to flight in September 1988. But the deepest lesson was not simply that cold rubber can fail. Challenger showed how catastrophe grows when warning signs are treated as inconveniences, when incomplete data is used to justify action instead of restraint, and when repeated near misses are mistaken for evidence of safety. The O-rings had eroded before. Engineers had written warnings before. The launch temperature was outside experience. The night before liftoff, the contractor had recommended stopping. The disaster lasted 73 seconds. The path to it took years. The warnings were there.